Dear students, in this class you will be studying about variable oxidation states of transition elements. Firstly, what is meant by oxidation state? That means the number of electrons which are accepted by an element or donated by an element or shared by an element during the formation of chemical bonds. For example, you can take sodium chloride. Here we have two elements. One is sodium, another one is chlorine. In this compound, there will be an ionic bond. During this formation of ionic bond, sodium will give one electron to become Na plus. So it is donating one electron and it is getting one positive charge. That's why it is donating one electron. That's why its oxidation state is +1. Similarly, in the case of chlorine, in the formation of ionic bond, chlorine will accept one electron from the sodium and it forms Cl minus. So it is accepting one electron. That's why this oxidation state of chlorine is -1 in the NaCl compound. Similarly, transition metals also show variable oxidation states because of the presence of number of unpaired electrons in the d orbital and 4s orbital. Here it goes. The 3D series, which is varying from scandium to zinc. Here, this is the electronic configuration of 3D series element. This is 4s orbital. This is 3D orbital. Valence electrons are involved in the bond formation. That's why we will take only valential electrons. This is valential electronic configuration. So, during these electrons are involved in the formation of chemical bonds. So this scandium is having 3 electrons in the 1 electron in the 3D orbit and 2 electrons in the 4s orbit. So this scandium can donate 2 electrons, minimum of 2 electrons to form chemical bond with the other elements. So if it loses 4s electron, it becomes +2 oxidation state. Similarly, if it loses 3D electron with the 4s electron, it shows it will become +3 oxidation state. If the scandium loses +2 electron, it will become +2 oxidation state. If it loses 3 valence electron, it shows +3 oxidation state. Similarly, for titanium can also show +2, +3. Here we have 4 electrons. So this titanium can donate 2 of the 4s electrons and any one of the 3D orbital, it shows +3 oxidation states. If the titanium loses 4s electrons and 3D electrons, it shows +4 oxidation state. Similarly, for vanadium can show +2 oxidation state by losing 4s electrons and +3 by taking one of the d electron with the 4s electron and +4 by taking 2 d orbital electrons with the 4s orbital electron and can show +5 oxidation state by taking all the 3d or electrons with the 4s electrons. So these are the 4 oxidation states of vanadium. Similarly, for chromium, you have to observe in the 4s orbital, there is only one unpaired electron in the 4s orbital. That's why this chromium can show +1 oxidation state. All these are unpaired electrons, so that chromium can show +1, +2, +3, +4 and +5. Finally, it can show +6 oxidation state. For manganese, here we have 2 electrons in the 4s orbital. That's why +2, +3, +4 with the 4s electron, +5 and +6 with the 4s electron and +7. Various oxidation states of manganese. Next, we will move on to iron. Iron is having total of 8 electrons in the valence shell. So, it can show +2, +3, 4 plus 5 plus 6 and plus 7 and plus 8 are not possible because these two paired electrons are not involved in the bond formation, because after d5 configuration, if you remove all the electrons of the iron except these two, we will be removing only electrons. We are not removing any proton. That's why effective nuclear charge increases. The number of protons in the nucleus increases when compared to the number of electrons. The positive charge increases. That's why that positive charge of the nucleus can hold these two electrons very tightly. That's why these two electrons are not involved in the bond formation. That's why iron will show maximum of plus 6 oxidation state. It will not show plus 7 and plus 8. Similarly, cobalt will also show plus 2, plus 3, plus 4, plus 5. Here there are two pairs of electrons are paired. With increase in the number of, when we remove these 5 electrons, there will also be a increase in the effective nuclear charge. That's why these paired electrons can't be removed easily after crossing d5 configuration. So the paired electrons of the d orbitals can't be removed when we move from d5 configuration to higher configuration. Similarly, for nickel, nickel will show plus 2, plus 3 and plus 4. Copper, here this copper is similar to chromium. It can show plus 1 oxidation state and it can show plus 2 and even plus 3. So these paired electrons can't be removed in the case of copper. Zinc shows only plus 2 oxidation state. These are the various oxidation states of 3D elements. Now we will see which is the most stable oxidation states among these. So for scandium there are two oxidation states. Among these, plus 3 is the most stable oxidation state, because if it loses 3 electrons, it gains D0 configuration, which is more stable. D0 means it will occupy orgon 18 3D0 4S0 configuration. That's why this scandium will be stable in plus 3 oxidation state. Similarly, for titanium also, titanium will be stable in plus 4 oxidation state because of the same reason, that is acquiring D0 configuration. And even for vanadium also, plus 5 is more stable because it acquires D0 configuration. That means inert gas configuration. That's why these three elements, scandium, any element, you can take any element which gives us a D0 configuration, will be the more stable oxidation state. For chromium, we will be having plus 1 to plus 6 oxidation state. Here, plus 6 is also more stable and plus 3 also more stable oxidation state. Because after removing 6 electrons from the chromium, it acquires D0 configuration because we are having potassium dichromate K2Cr2O7. Here this is a stable compound which is a D0 configuration. Similarly, we have many compounds of chromium plus 3 which are stable. Similarly, manganese will be stable in plus 2, plus 4 and plus 7. Here we are using KMnO4 as oxidizing agent. That's why KMnO4 is a stable compound. Manganese can donate 7 electron and form a stable compound. That's why plus 7 oxidation state of manganese is more stable, and even to plus 2 and plus 4 are also stable oxidation states. Similarly, if you go to iron, iron will be stable in plus 2, plus 3 and plus 6 oxidation state. So, these are the stable oxidation configurations of 3D series. And cobalt will be in the plus 2 and plus 3 are stable. For nickel, plus 2 is more stable electronic configuration. For copper, plus 2 is a more stable configuration. Zinc also plus 2 configuration. Here you can observe after D5 configuration, there will be a one trend, that is lower oxidation states will be stable after D5 configuration. Before D5 configuration, higher oxidation states will be stable because they acquire D0 configuration. Similarly, if it loses 2 electron, manganese, if it loses 2 electron, it will be D5 configuration. So this is exactly off-filled electronic configuration, which is more stable as D0 configuration. Off-filled, full-filled and D0 configurations are more stable. So Mn plus 2 is also stable oxidation state because it gives us D5 configuration. Similarly, if you go to zinc if it leaves 2 electron, it will be D10 configuration. So D10 configuration means completely filled. That means the oxidation states which gives D0, D5, D10 configuration are the more stable oxidation states. Here you have to observe one more thing, the minimum oxidation state. The minimum oxidation state is obtained by losing 4s electrons only. After losing only 4s electrons, you will get a minimum oxidation state. In generally, it is plus 2 because most of the D block elements are having 2 electrons in the 4s orbital, which can be easily available for the formation of chemical bonds, except chromium and copper. These can show plus 1 oxidation state. In generally, we can say minimum oxidation states can be obtained by losing 4s electrons in the 3D series. Similarly, the maximum number of oxidation states can be obtained by losing both 3D and 4s electrons up to D5 configuration. After D5 configuration, there will be an increase in effective nuclear charge. That's why the paired electrons can't be removed easily. So up to D5 configuration, the maximum oxidation states can be obtained by losing D electrons and S electrons together. Now we will move on to 4D series. See, 4D series is varying from yttrium to cadmium, that is atomic number 39 to 48. This is the electronic configuration of 4D series. This is 4D orbital and this is 5s electron. Here also the minimum oxidation states can be obtained by losing 5s electrons and maximum oxidation states can be obtained by 5s electrons and 4D electrons together. Here this is the vertical column, here it is in the horizontal rows. So yttrium can show plus 3 oxidation state, which gives us D0 configuration, which is stable. For zirconium, which is plus 2 and plus 3 are more stable electronic configuration. For niobium, plus 3 is the most stable oxidation state. For molybdenum, you can observe here plus 2 and plus 3 oxidation states are more stable, and molybdenum cannot show plus 1 oxidation state. We know that the chromium here, chromium, molybdenum and tungsten are in the same family, but molybdenum and tungsten cannot show plus 1 oxidation state because of the electronic configuration. Molybdenum and tungsten will follow the regular pattern of electronic configuration, whereas chromium will follow anomalous electronic configuration. For technetium, plus 3 is the most stable oxidation state. For ruthenium, you can observe here plus 6, plus 7, plus 8 are the stable oxidation states. For iron, you may observe iron, ruthenium and osmium belongs to the same group. Here, iron will be in the plus 2, plus 3 oxidation states are the most stable with the plus 6 configuration. Highest is plus 6 configuration and it is also stable configuration. Whereas in case of ruthenium, it is showing plus 7 and plus 8 configuration because when we move down the group, there will be addition of one more orbital. That means then there will be a number of electrons in the inner orbitals will increase. Therefore, the screening effect increases. When compared to effective nuclear charge, screening effect will be maximum in case of 4D and 5D series when compared to 3D series. That's why the valence electrons means 4D and 5s electrons are staying away from the nucleus. Therefore, those electrons can be easily available for the formation of chemical bonds. That's why ruthenium will show higher oxidation states, that is plus side oxidation state. Similarly, for the same reason, rhodium will also show plus 5 and plus 6 oxidation states as stable and with the plus 2 oxidation state. Palladium plus 3 is more stable oxidation state. For silver, plus 2 and plus 3 are more stable oxidation state. As in the case of zinc, cadmium will also show plus 2 oxidation state. So, with this, we'll move on to 5D series. This is the electronic configuration of 5D series, which is varying from lanthanum. Here we have a 14 elements which are kept in the F block elements. Then osmium to mercury. We'll be having 10 elements in the 5D series. This is 5D orbital and this one is 6s orbital. Here also the minimum oxidation states can be obtained by losing 6s electrons, and the maximum oxidation states can be obtained by losing 5D and 6s electrons. So if you write the oxidation states for these elements, so lanthanum can show plus 3 oxidation state. This gives a D0 configuration. Similarly, scandium and yttrium. Osmium will be stable in plus 2 and plus 3 oxidation state. Plus tantalum will be stable only in plus 3 oxidation state, and tungsten will be stable in plus 3 and plus 2 oxidation state. Rhenium will be stable in plus 3 oxidation state. Osmium will be stable in plus 2 and higher oxidation states. Here, iridium. Iridium will show plus 2, plus 4, plus 5 and plus 6 oxidation state. Platinum will be stable in plus 3 oxidation state. Gold will be stable both in plus 2 and plus 5 oxidation state. Mercury will be stable only when plus 2 oxidation state. So stability of these compounds can be studied by the formation of oxides. For example, here I told that a plus 8 configuration is more stable. So for osmium, we will be having a compound osmium tetroxide. Similarly, for tungsten will be stable in plus 6 oxidation state also. We'll be having a compound tungsten tetroxide minus 2 ion. In this tungsten is in plus 6 oxidation state, which is more stable. You can write the oxidation states of the D block elements. To summarize this, minimum oxidation states can be obtained by losing only s orbital electrons, and maximum oxidation states can be obtained by losing both d electrons and s electrons. And while studying the stability of oxidation states which gives D0, D5 and D10 configuration in 3D series are more stable, and lower oxidation states are stable in 3D series, whereas higher oxidation states are stable in 4D and 5D series.